Hello. In this demo, I would be going through the notebook of TensorFlow tensor operations tutorial. And after the introduction cell, in the next cell, I install or upgrade TensorFlow to the latest version, and I also install Matplotlib library and Seaborn for visualization. The -q flag keeps the output quiet so we don't unnecessarily installation logs. Next is import libraries and setup. Here I import TensorFlow, NumPy, Matplotlib library and Seaborn, and I also print the version of GPU if a GPU is available. I also set a random seeds for reproducibility so results are consistent every run. Next is this cell creates a zero-dimensional tensor called a scalar using a tf.constant of 42. I print its value shape which is empty and rank which is 0 since it has no dimension at all. Next here I create a one dimension tensor or vector from a list of 5 numbers. I print its shape as 5, and its rank as 1 showing it is a single row of values. Next, this cell creates a two-dimensional tensor or matrix with 2 rows and 3 columns. I print its shape as 2, 3 meaning 2 rows and 3 columns and confirm it as rank 2. Here I create a three-dimensional tensor that can represent a stack of matrices or an RGB image. Its shape is 3, 2, 2 meaning 3 depth layer each with 2 rows and 2 columns. This cell uses a Matplotlib library to draw a visual diagram of a scalar, vector, matrix and 3D tensor side by side. The visual help build intuition of how data is structured at each dimension level. Next, I create a tensor field with all zeros using tf.zeros and all ones using tf.ones. Zeros are used for bias initialization in neural network and ones are used for mask and constant scaling. Next is this cell creates a 4 cross 4 matrix using a tf.I and a diagonal matrix from a vector using a tf.linealg.diag. Identity matrices are used in a linear algebra and a baseline in matrix. Next here I use a tf.range to create a step-based sequence and tf.linespace to create evenly spaced values between two numbers. Next cell, this cell generates a random tensor with values drawn from uniform and normal distributions using tf.random.uniform and tf.random.normal. In the next cell, I implement a Xavier and he weight initialization schemes for neural networks. Xavier is recommended for sigmoid and tanh activations while he initializes it's better suited for relay activations. Next cell, in this cell plots histogram of Xavier and he initializes weight side by side. And the visualization confirms that each scheme produces a different spread of values. Here I list and demonstrate the common TensorFlow data types using float 16, float 32, float 64, int 32 and bool. Next, this cell converts a float 32 tensor into int 32 and other types using tf.cast. Next, I compare the memory consumed by float 16, float 32 and float 64 tensor of the same shape. Next cell, this cell demonstrates how to inspect a tensor using its shape, ndim, dtype and size and attributes. In the next cell, I convert between TensorFlow tensors and NumPy arrays using .numpy and tf.constant. I also show how Python scalars are handled. In the next cell, this cell shows the TensorFlow automatically accepts NumPy array in its function without explicit conversion. In the next cell, I access individual element of a 2D matrix using row and column indices. Both matrix positive indexing from the start and negative indexing from the end are supported. In the next cell, this shows how to extract an entire row, entire column and submatrices using a slice notation, as we can see here. Next is this cell demonstrates a tf.gather. This cell demonstrates a tf.gather to select specific rows from a matrix using an index list. Gather is heavily used in embedding lookups. I use next a tf.gather nd to select items at specific row column coordinates provided as a list of pairs. Next, this cell creates a boolean mask by applying a condition like data greater than 0, then filters the tensor using tf dot boolean mask. Next cell here, I reshape a flat 1D tensor of 12 elements into 2D and 3D shapes using tf.reshape. The total number of elements must remain the same, and this operation is used constantly before linear layers. In the next cell, this cell uses -1 as a wildcard in reshape, so TensorFlow automatically infers the missing dimension. It is a convenient shortcut when you know all dimension except one. In the next cell, I transpose a 2D matrix using tf.transpose, and I also reorder dimension in a 3D tensor using the perm argument. In the next cell, this cell adds a new dimension of size 1 to a tensor at different position using a tf.expand.dimensions. Yeah. Let's go to the next one. Here I remove all size -1 dimensions using tf.squeeze and also squeeze a specific axis. In the next cell, this cell joins two tensors along a row using axis is equal to 0 and along the column using a axis equal to 1 with tf.concat. Next cell, I stack multiple 1D tensors into a 2D tensors using tf.stack, which create a brand new axis. And then this cell shows all basic arithmetic operations, as we can see here: addition, subtraction, multiplication, division, and power applied element by element between two tensors using Python operators. Here I show the tf.add, tf.subtract, multiply, and other operation functions that match the Python operators. They both give the identical results, and the function forms are useful in functional programming. This cell applies math functions like tf.exponential, tf.math.log, and tf.square root to tensor element by element. Next is trigonometry function cell. I compute sine, cos, and tan of angle values using TensorFlow's trigonometric functions here. In the next cell, this implements and compares the main four activation functions like sigmoid, tanh, ReLU, and leaky ReLU using tf.nn functions, as we can see in this cell. Next cell is I apply softmax to raw logits to convert them into probabilities that always sum to 1. In the next cell, this plots all 6 activation functions: sigmoid, tanh, ReLU, leaky ReLU, ELU, and GLU in a grid form. Next is broadcasting scalar and row vector. This cell shows how a scalar is broadcast to every element of a matrix and how a row vector is added to every row. Next, I demonstrate column-wise broadcasting by using a 2,1 tensor that gets added to each column of a 2 by 3 matrix. The key is shaping the vector with a trailing dimension of 1. This cell stimulates the dense layer computation y is equal to wx plus b, where the bias vector is broadcast across all samples in the batch. Next is I multiply two matrices using tf.mat multiplication and verify the output shape. Matrix multiplication is the single most important operation in deep learning. This cell shows the cleaner at operator for matrix multiplication and expand it to a batched multiplication over 32 matrices at once. Here I compute the dot product of two vectors using a tf.tensor.dot with axis equal to 1, and this is the output. Vector norms. This cell computes L1, L2, and infinity norms using tf.norm. And next I perform eigen decomposition on a symmetric matrix using tf.lineall.i, which returns real eigenvalues and eigenvectors. Next, this cell applies SVD to a 4x3 matrix using a tf.lineag and that line, returning a US and VH matrices. Next, here I introduce tf.einsum with simple operations like summing a vector with I and all those transposing a matrix. Next, this cell uses einsum of a dot product with whatever and an output product. So next is einsum matrix multiplication. I perform matrix multiplication, use the einsum function that we can see here, and verify it match with the mat.mul. Yeah. Next is this cell uses INSUM for batch matrix multiplication and the attention score computation from the transformers. Next is INSUM cheat sheet. Here I print a comprehensive cheat sheet of common INSUM notation, which are sum, transpose, trace, dot product, outer product, matrix multiplication, and match multiplication, all to refer kind of in a single table. Next, this cell applies a TF dot reduce sum and TF dot reduce mean both globally and along specific matrix. Next, here I use the reduce, max, min and all those aggregate kind of functions to perform the similar functionality. Next, this cell shows a keep dims is equal to true to preserve the number of dimensions after a reduction. Next, I manually implement a fully connected dense layer as y is equal to activation and the form with operator, the formula and the whole function is here. Next is this cell computes softmax probabilities from logits and then calculates cross entropy loss using the functions that we can see in this whole function definition. Here I implemented the full scale dot product attention mechanism from a transformer paper using INSUM and softmax. The formulas of all these are the one which we can see here, and then these prints those values. And this is exercise 1 where I create a 4 cross 4 matrix, extract its diagonals and compute the trace. Next, this is a shell which shows the solution to exercise 1 step by step. I create the matrix using tf dot reshape and extract diagonal, compute the trace and also show the equivalent and some approach. In the exercise 2, where I am asked to implement batch normalization from scratch, the task is to compute the mean and variance across the batch dimension and normalize the input tensor. Next is the solution implements batch normalization by computing the mean and variance using tf dot reduce mean and tf dot math reduce variance. Then normalize and add epsilon for numerical stability. Next is this cell implements a full two-layer neural network forward passing using He initialization, ReLU activation in the hidden layer and softmax in the output layer. The final cell repeats the softmax and cross entropy computation as a practice review. It reinforces how raw logits are converted to probabilities and how the loss is computed for a batch of prediction. And that's it with the demo of this whole notebook, and thank you.